Hello all and welcome to the Basics.Academy channel. In this video, we are going to look into MEV mechanics plus commit reveal pattern. Again, we are going to start with our AI tutor, wherein I will paste in the deliverable which we want for today, and accordingly it will ask us questions and walk us through the implementation phase. Let us do that. Let me copy this. I'm going to Cloud Code. Inside Cloud Code, all projects. And here we have plan executor. Let me paste this and we get started. Finding tools.
Welcome back. Great to have you here. Today we are diving into MEV mechanics and the commit reveal pattern, and your deliverable is CommitReveal.sol with Foundry tests. Before we write a single line of code, I want to assess where you are at. So tell me in your own words, what is MEV?
MEV is maximum extractable value.
Good start. That's the name, but I want you to go deeper. Who extracts it and from where exactly?
Who extracts it? The miners, and it is extracted from the transaction memory pool. Who extracts it? The miners, and it is extracted from the transaction memory pool.
Good miners or validators in proof of stake, extracting value from the mempool. Now here's the key question: how does a miner actually extract that value? What power do they have over transactions sitting in the mempool?
Depending on which transaction is tipping or giving more transaction fees, the miners can selectively pick up those transactions and add that into a block, making their returns of including transactions in a block maximum. In this way, the miners or validators extract the maximum extractable value.
That's correct, but miners have an even more powerful ability than just selecting transactions. They can also reorder them, insert their own transactions, and even censor certain transactions entirely. With that in mind, can you think of a specific attack where a miner, or even just a bot, sees your transaction in the mempool and profits by placing their own transaction right before yours?
This is possible in case of you are trying to do a large swap from any given pool. If a bot or miner sees this, they can put their transaction just before your transaction and make sure that the return which you will get from the swap is less as expected while you are doing the swap. So this is a possibility when it comes to transaction reordering and inserting their transactions just before the user's transaction.
Excellent. What you just described is called frontrunning. Now, there's a closely related attack that goes one step further. The attacker places a transaction before yours and another one after yours. Do you know what that attack is called?
Is it sandwich attack? Is it sandwich attack?
Exactly, a sandwich attack. Now let's go mechanical. Can you walk me through step by step what happens in a sandwich attack on a DX swap? What does the attacker do in each of the three transactions?
Number 1, just before the large swap happens, the attacker will try to create a price drift in such a way that the swap which is performing a large transaction will be in loss. Number 2, once that large swap executes with maximum loss, then in the third step, the attacker again sends another transaction in order to get advantage of the price drift and get as much token as possible from the DEX pool.
You have the right shape. Let me make it more precise. In step 1, the attacker buys the same token you are about to buy. This pushes the price up due to the AMN curve. In step 2, your transaction executes at that now worse price. In step 3, the attacker sells the tokens they just bought at the inflated price, pocketing the difference. So here's my question: what property or AMMs makes this attack possible in the first place?
The property of AMMs, such as constant product formula in case of Uniswap, makes this attack possible.
Correct the constant product formula x times y equals k. But why specifically does that formula make the price sensitive to transaction ordering? Think about what happens to the price when someone buys a large amount from the pool.
Since the price is x times y equal to k, whenever somebody buys a token, say x from the pool, then the price is adjusted as per the constant product formula.
Right? So when someone buys token X from the pool, the reserve of X decreases. For the product to stay constant, what must happen to the reserve of Y, and what does that do to the price of X?
The reserve of x decreases. I'm not sure.
Yeah, baby. Yeah. That's fine, let's reason through it. If x times y equals k and x decreases, then y must increase to keep k constant. Now the price of x in terms of y is y divided by x. If x goes down, y goes up. What happens to that ratio?
Okay. If x goes down and the price of x is y divided by x, if x goes down, in that case, the value of y will inflate.
Almost there. Y increases and x decreases, so the ratio y divided by x gets larger. That means the price of x goes up. And that is exactly why the sandwich attack works. The attacker's front run by raises the price of x. So your swap executes at a worse rate. Does that click?
Yes, got it. So when the price of X goes up, the large swap executes at a loss. And then after that, the attacker again performs another transaction to get the difference since the price of X has gone up.
Perfect. You now understand the sandwich attack mechanically. Now let's connect this to your deliverable. The commit reveal pattern is one defense against this. Before I explain it, take a guess. How do you think hiding your transaction intent could protect against a sandwich attack?
By hiding the amount that I want to swap and the token which I am willing to buy in.
Exactly. If the attacker cannot see what you intend to swap, they cannot front run you. Now, here is the key design question on a public blockchain. All transaction data is visible. So, how would you actually hide your swap intent on chain?
By using the idea of Merkle proof, we can generate a proof and then that proof can be decoded on chain to get the amount from it. This is just a wild guess.
Good instinct cryptographic hiding is the right direction. But commit reveal doesn't need Merkle proofs. It uses something even simpler. Think about a hash function. If I submit only the hash of my swap parameters, what can an attacker learn from that hash?
The attacker can learn nothing.
Exactly, the hash reveals nothing about the original data. So that is the commit phase. Now, in the reveal phase, you later submit the actual parameters. The contract hashes them and checks they match your earlier commitment. Here is my question: what stops an attacker from front running you during the reveal phase when your actual swap parameters finally become visible?
In the commit phase, we are submitting a hash. In the reveal phase, we are submitting the actual transaction parameters. What does stop the attacker from front running the reveal phase? Does the hash include a random value which is passed at runtime?
You've hit the high reveal. The reveal invisible in the temple. We accuse your commitment. The is tied to your address. What happens if the attacker tries the reveal data?
The attacker sees your reveal transaction in the mempool, but the commitment was submitted in the commit phase tied to your address. If the attacker tries to copy your reveal parameters and submit their own reveal transaction, what happens? Can they steal your commitment? They cannot because the commitment is tied to my address, and in the reveal phase we are going to use msg.sender and that message.sender will be checked with the address which is tied to the commitment.
Exactly, the commitment is bound to msg.sender, so an attacker copying your reveal parameters will fail the check their address won't match your commitment. Now, one more thing is needed in the commit hash to prevent a different attack. What if an attacker pre-computes a rainbow table of common swap amounts and just looks up your hash? How would you prevent that?
By passing in a nonce value while submitting the commitment.
Perfect. A nonce, or often called a salt, makes every commitment unique and unpredictable, defeating rainbow table attacks. So now you have the full commit reveal structure. The commitment hash includes the swap parameters, the user's address, and a secret nonce. Let's now build the contract. What should the data structure for storing a commitment look like in Solidity?
We can use mapping from address to bytes 32 to store commitments.
Good start. A mapping from address to bytes 32 stores the hash. But we also need to know, has this commitment already been revealed? And should there be a time window, a deadline after which a commitment expires? How would you extend the data structure to track those two things?
We can use a structure struct commitment which has bytes 32 hash and then bool is revealed and then uint 64 then
Excellent, that struct is exactly right. Now the mapping becomes address to commitment. Let's move to the commit function. What parameters should it take, and what should it have?
okay, the caller passes its 32 hash the contract take by the contract stores them in a structure in the mapping of commitment structure and emits committed event.
Good, but should the caller pass in the hash directly, or should the contract compute the hash from the raw parameters? Think carefully. If the caller passes in a pre-computed hash, can the contract verify it was constructed correctly? Good instinct. Now be specific. What exact parameters should the caller pass into commit so the contract can compute the hash? Remember, the hash needs to include swap parameters, the user's address, and a nonce. What are the swap parameters for a pool swap?
The parameters are token in, token out, amount, amount minimum, slippage, nonce. Token in, token out, amount, then minimum amount, slippage, and nonce.
Excellent, that's a thorough list. Note that minimum amount out and slippage are actually expressing the same thing. Minimum amount out is already the slippage adjusted value. So we can simplify to token in, token out, amount in, minimum amount out, and nonce. Now the contract does not store all these parameters. It only stores the hash. So how does the contract compute that hash from these parameters?
We can make use of CommitReveal 256 abi.encode token in, token out, amount, amount out, min, and nonce.
Almost perfect, but you're missing one critical ingredient. You said earlier that the commitment must be tied to the user's address. So what should you add to that KCAC 256 call?
We should add a msg.sender.
Perfect. So the full commitment hash is KCAC 256 of abi.encode of msg.sender, token in, token out, amount in, amount admin, and nonce. Now let's write the full commit function. Also, should a user be allowed to overwrite an existing commitment? What check would you add?
I'll write the full commit function, the correct parameters, the hash computation, the check that prevents overwriting an existing commitment, storing the commitment struct, emitting an event. Okay. So here we're going to create our contract CommitReveal.sol. Split right. Let me copy keystore things. Then our contract is CommitReveal. Here you're going to define a struct commitment which has bytes 32 hash, then bool is revealed, and then new end 64 deadline. Then we have a mapping from address of B user to mapping, and that mapping is of commitment public commitment. I think we should have an array of commitments, not just one commitment. So we must have an array of commitments. Then we will also maintain another mapping address user. I think it should be a nested mapping from address user to index to commitment. This user 2 bytes 32 commitment hash. It will be, this will be the value. Mapping. Here we will have queued 256 index. So this will give us commitment index. This will give a commitment hash at index. Then we will have our event committed, which will take in address indexed user, then bytes 32 commitment hash, and then show in 64 dead life. Then we have our function commit external commit external. This will take in the parameters plus token in address token out humid 256 amount into 56 amount out minimum, then event 256 nuts. And here first limit compute, it's 32 hash, which will be our commitment hash, and this will be abi.encodePacked. Here inside encode we will use first message dot sender, then token in, then token out, then amount, then throw it out min, and then nonce. After this we'll store so commitments of message dot sender dot push the commitment hash. Then we are going to get the index at which it is pushed. So going to by 6 index is equal to commitments of message dot sender dot length minus 1. And then at last we'll say commitment hash at index of user. This is the index is equal to the hash. So what we can do is, from this commitments given the user address, we will get all the commitments which the user has submitted, and from using commitment hash at index, so given the user address and the index, we can get a specific commitment hash from this commitments structure L. Now how to check if the user has already committed the same hash? So for that For that, first we are pushing the hash. I think this condition will be overridden. We keep this. Here is the commit function implemented. Sorry, I haven't added the overlighting existing commitment check because here the user can add multiple commitments.
Good design thinking allowing multiple commitments? But look at your push call, you're pushing a bytes 32 directly into an array or commitment structs. What should you push instead? And where is the deadline coming from?
Okay, got it. So here there is no need to push a hash. Commitments of msg.sender dot push. Here we are going to push commitment has hash which will come from above. Then is reveal is false. At last deadline is the past in deadline. This is fixed. Then it says what should you push instead. This is fixed. The commitment hash at index mapping is redundant. You can already get the hash via commitments message.sender or index.hash. Commitments message.sender of index. Right. Then after that you are not setting deadline. You forgot to emit the committed event. Noted. This is redundant. What else? What else do we have? So there is no need for this. Either we emit the committed event with message.sender, and then hash is the commitment hash, and at last the deadline. Got it. Done with the fixes. Here is the updated code.
Good progress. But deadline is used in the function and never defined, it won't compile. Should the caller pass in the deadline, or should the contract calculate it automatically from block.timestamp plus a fixed window?
So abi.encode message sender token on Nonce. No, the deadline must be passed as a function argument, which I have already done.
Look again carefully at your function signature. Is deadline listed as a parameter? Perfect, that compiles cleanly now. But I want you to think about one thing. Should you use abi.encodePacked or abi.encode for the commitment hash? And why does the choice matter for security?
We must use abi.encode because it makes all the arguments padded to 32 bytes, and it is recommended over abi.encodePacked.
Exactly right. abi.encode pads everything to 32 bytes, making each argument unambiguously separated, no collision risk. Good catch. Now let's move to the reveal function. What parameters should reveal take, and what checks must it perform before executing the swap?
Reveal should take in the hash that would be the input argument to reveal.
Think more carefully. If reveal takes in the hash directly, how does the contract verify that the hash matches the original commitment? The whole point is to prove knowledge of the original parameters. What should the caller actually pass in?
The caller should actually pass in all the input parameters which he has already passed to the commit function.
Exactly. The caller passes in all the original parameters token in, token out, amount in, amount admin, nonce, and the commitment index. The contract recomputes the hash and checks it matches. Now what are all the checks reveal must perform before executing the swap? List them in CEI order.
It must check that the deadline has not passed. Second, it must check is revealed is false.
Good deadline not passed, and is revealed is false. But you're also recomputing the hash from the caller's parameters. What check must you perform with that recomputed hash against the stored commitment?
That recomputed hash must be matched with the stored commitment hash.
Perfect, you have all three checks. Now write the full reveal function in Solidity. Include all three checks, mark is revealed as true in the effects phase, and leave a comment where the swap interaction would go.
So we have our function reveal, which takes in all these parameters, plus an index. This will be the external function. So here we will fetch the commitment from the storage. So commitment is equal to commitments of message.sender, then pass in the index. Once we have this, let me add custom errors. Error deadline crossed or past deadline. The second check is error already revealed. After that, error hash mismatch. So first, as we have got hold of the commitment from the storage, first we'll check if commitment dot deadline is less than or equal to block dot timestamp. Or if commitment dot deadline is greater than or equal to block dot timestamp, then revert past deadline. After that, we check if commitment dot is revealed, revert already revealed. Then we check if commitment, then v bytes 32 calculated hash is again equal to the same thing as we are passing all these values in the function argument. Then we check if calculated hash not equal to commitment dot hash, then in that case revert hash mismatch. After that, so this is the check part is done, including all three checks, the effects, phase, state change, and leave a comment when the swap interaction would go. Check effects interaction. So this is the check part. Then we have the effects part. Inside effects, what we are going to do, you are going to set so this way commitments of message.sender of index dot is revealed is equal to then inside interaction swap will happen here. Commitments check effects, I think this should also emit an event revealed and press indexed user see hides 32 commitment hash, then followed by event 64 at last we met revealed with message.sender and the hashes can be calculated hashes. Here is the reveal function.
Really solid structure. But look at your deadline check. You revert when deadline is greater than or equal to block.timestamp, but that means you revert when the deadline has not passed yet. What should the correct comparison be?
if commitment.deadline, and when the deadline will pass, and block.timestamp is greater than the deadline. Okay, so deadline is, let's say deadline is 26th June and block.timestamp is 27th June. So
Actually, your condition is equivalent and correct, well spotted. But there's another issue. You declare commitment equals commitments at msg.sender index without specifying storage or memory. Which keyword should you use and why does it matter here?
you should use the keyword storage here, and then here directly we can write to storage. Should use the keyword storage here, and then directly write is revealed to the storage. So in this case, let me, if log.timestamp is greater than commitment.deadline, never past deadline, here is the updated function.
That is keen and correct. But look at your reveal function signature. You have deadline as a parameter, but you never use it in the function body. The deadline is already stored in the commitment struct. Should it be a parameter at all?
No, it shouldn't be a parameter at all.
The code contract logic is now complete and correct. Now let's think about the Foundry tests. What are the three most important test cases you should write for this contract?